Hello, everyone, and welcome to the second episode of the CLSE Hangouts. We are going to be doing these at least once a month, except in August, which we're taking off because of the International Astronomical Union meeting. And each month we are inviting you in to see what all the Center for Lunar Science is up to. And with me today is our PI of our program. David Kring is joining us, and as always, I have my co-host Andy Shaner with me from the Lunar and Planetary Institute. If you want to join in, ask questions, we are here for the next 30 minutes to help you understand what all this project is about. David, you are the principal investigator of this project. Can you tell our audience what that means and what all you're looking to accomplish with the CSLE?
Sure.
CLSE, sorry.
That's quite all right. So briefly, we have several segments to our program. We address high priority science. We try to integrate that science with NASA's exploration objectives, and specifically we're talking about its human exploration objectives. And we have a training component where we're actually trying to train high school, college, and graduate student as they matriculate into the workforce, hopefully with NASA and supporting universities. And of course we have an education and communication program, of which this is an example. On the science side, we're very interested in understanding the collisional evolution of the solar system. And one of the key benchmarks for understanding that is the impact cratering record of the Moon. Whereas geologic processes on the Earth like plate tectonics, volcanism, erosion are constantly destroying or resetting the geologic record on the Earth. The Moon has preserved that impact cratering record, and so it's in some sense our Rosetta Stone for understanding this. We mirror that or complement that with a study of asteroids, which is the dominant object hitting the Earth, the Moon, and other inner solar system planets. So that basically represents our core science. If you're going to have a successful program, you have to have an absolutely world-class science program, and that's it for us.
And your center is one of the many different survey nodes, part of NASA's entire network of organizations that are looking to explore our solar system. Where do you fit in, and how does the work that you're doing complement the other work going on throughout this network of centers?
The network of centers are designed to address issues associated with the Moon, with asteroids, and in particular near-Earth asteroids, and the moons of Mars moons Phobos and Deimos. Most of the team's work is associated with either the Moon or the asteroids. We only have taken the first steps to understanding Phobos and Deimos, in part because in the exploration timeline they are a little bit farther down the path. So we're prioritizing our studies of the Moon, and behind that asteroids, except to the extent that asteroids inform us about what's going on the Moon, and then down the road Phobos and Deimos.
And a lot of people get a little bit confused by the fact that you have Phobos and Deimos in your arsenal of things to be studied, but stop before you get to Mars, stop at the atmosphere. And Phobos and Deimos are kind of unique as far as inner rocky body moons go. And can you help our audience who may not be familiar with these objects understand how they fit in with asteroids and the Earth's moon?
Sure. Phobos and Deimos are relatively small moons. Mars moons are not comparable in size to, for example, to the Earth's moon, which is incredibly large. Phobos and Deimos are small bodies that probably have their origin in the asteroid belt or through a series of geologic processes similar to those that form the small or minor planets of the asteroid belt. And at some point in time, which my colleagues and I constantly debate, but at some point in time they seem to have been captured by Mars. Now, one of the reasons that they are attractive, at least as an initial exploration component, is that astronauts, if they were to explore them, do not have to descend through the atmosphere of Mars to the surface. They don't have to, more importantly, try to escape the gravity well that a planet as large as Mars represents. And so it would be a way to establish, if you will, a foothold in the Mars system in advance of a bigger project.
And like so many of the other asteroids and small rocky bodies out there, Phobos and Deimos, they're lumpy potatoes. They're not even actually round bodies yet, which changes the physics of, well, not the physics, the geology of them somewhat. How might we expect these and other, well, potato-shaped objects to be different from our own moon and the bigger round objects?
Okay, let me start with, in answering that, start with the moon, because it is the moon in some sense is very much like the Earth in that it is large enough to have become internally hot enough to melt and differentiate. So the moon has a small core, it has a mantle, and it has a crust. So in that way, it's very much similar to the Earth. Again, though, because it preserves a different point in that evolution, the moon can tell us things about the formation of planets like the Earth or Mars in a unique and valuable way. In contrast, many asteroids are what planetary scientists call primitive bodies. They accumulated from relic dust and gas from a solar nebula that once surrounded the sun. Those small dust and gas accreted to form these small bodies, planetesimals or minor bodies. In most cases, those bodies accreted to form the larger planets like Mars and the Earth. But some of them did survive that planetary accretional process and for the most part, dominated the zone between Mars and Jupiter, and were not further processed except through collisions or impact cratering processes. So they're primitive in that they contain evidence of those incredibly ancient solar system processes. Now, before somebody jumps on with a sharp question, but what about Vesta? I do need to explain that some of those objects, not all of them, but some of them did get large enough to get hot enough to differentiate, just like the Earth and the Moon, but many of them contain that primitive solar system history.
And it really comes down to how round and massive is it. Easy rule of thumb is rounder the object, the more likely it is to be massive enough to have had more interesting physics and geophysics taking place.
Yeah, that's correct. Get hotter and potentially differentiate. Now, although CLSE and the survey program that we're a part of is not investigating the same topics at the Dawn mission. Since we're interested in what NASA is doing more broadly, the Dawn mission is actually comparing Vesta with Ceres, two of the larger asteroids, both relatively round, one of which seems to have differentiated in a much different way than the other. So there is a lot to learn, both on the primitive end of the asteroid spectrum as well as on the more evolved end of the asteroid spectrum.
And part of what makes this so interesting is that the asteroids, while we think of them as being this homogeneous belt, actually formed in a fairly unique part of the solar nebula where essentially the sun went from baking things dry to leaving them, well, with the potential, like Ceres, to be icy. Can you tell us a little bit about how these different populations were able to grow up in the early solar system?
Well, we think that these small planets, which again we call planetesimals, were probably scattered throughout a large part of what's now the solar system. But the only remnants of that population, or I should say the principal remnants of that population, are between the orbits of Mars and Jupiter. So there was probably a population of them in the vicinity of the Earth, but they simply were accreted to form the Earth, or were scattered out of the solar system. But those that are formed between Mars and Jupiter did seem to survive. And there's some dynamical reasons that we suspect may be behind that. As you say, not all asteroids are the same. The asteroids at the inner edge of the belt do seem to be a little bit drier than those in the outer belt. And in fact, that's one of the reasons that Deimos, in the case of, again, Mars moons, is attractive, because it does seem to have some of the chemical and mineralogical properties of some of the outer solar system asteroids.
And with the CLSE and with Survey itself, exploration is at the heart of where you're going with a lot of the research. As we look at Phobos and Deimos, you see the pathway to Mars. As we look out at the asteroid belt itself, we see the pathway for folks who are looking like planetary resources to go out to the asteroid belt. In looking at all of these different pillars, how do you fit them together within CLSE?
Well, we spend a lot of time studying potential targets for those exploration efforts. So, for example, just a few minutes before we started, I was having a conversation with a visiting group of graduate students, 7 of them, from around the world, who are spending the summer with us, studying locations on the lunar surface where we hope to actually collect samples and return them to Earth. The concept that they're investigating is one involving a robotic rover that traverses across the lunar surface, stops at stations that the students themselves are identifying this summer, collect samples, return those samples to an ascent vehicle, which then leaves the moon's surface and rendezvous with astronauts in lunar orbit. And then the astronauts will recover those samples and return them to Earth. So that's one of the ways in which we are integrating our science activities, which in this case is a geologic study of the lunar surface, with exploration activities, which is trying to develop an actual mission concept that involves both the nation's robotic assets as well as its human assets.
And early in this hangout, you mentioned the importance of studying craters, and the way they tie into this, they actually come in over and over and over between age dating, looking for lunar skylights, just trying to get at the variations in the thickness of the crust when you're looking at bodies like the moon. Are the students looking to take advantage of any of these variations in their explorations, or do you have other teams that are looking at that?
Yeah, so impact cratering, so let me say some high-level things. Impact cratering is the dominant geologic process affecting planetary surfaces, whether that be the moon, asteroids, or Mars. Volcanism is a close second, but impact cratering is just incredibly important. It was far more important earlier in solar system history. So there was a period of intense bombardment of all of the inner solar system planets, somewhere between 3.8 and 4.5 billion years ago. Trying to understand the details of that is one of NASA's highest science objectives. And so one of the ways that you tackle that is you go to representative impact sites on the lunar surface, collect samples, bring those samples back to Earth, analyze them so you can determine the ages of those impact events. You know, did all of them occur at the same time? Did all of them occur over a 200 million year period, and so on and so forth. There are a lot of other science objectives that have been articulated by the National Research Council for NASA for future lunar exploration missions, and the students are basically following the recipe that the National Resource Council developed. And in previous studies that students have done here with our team, they've identified the Schrodinger impact site as the single best place to accomplish the most science on the lunar surface. And that is, in fact, illustrated in this diagram behind me. I don't know to what extent you can see it, but you may see that there is an impact basin being formed over one of my shoulders. That is the Schrodinger basin being formed on the lunar far side. The Schrodinger basin is about 320 kilometers in diameter. It sits inside the South Pole Aitken Basin, which is 2,500 kilometers across, and the largest, oldest basin on the Moon, and in fact, the largest impact basin that we know of in the inner solar system. So, yes, previous studies by these similar groups of interns have focused our attention to some specific places on the lunar surface, and the Schrodinger Basin on the lunar far side is right at the top of the list.
Now, there's lots of teams that are currently getting ready to explore the Moon with the Google Lunar X Prize. We have OSIRIS-REx, which is off to get a sample return of asteroid Bennu. With all of these different missions out exploring, what are some of the major research goals that you hope to see solved in the next 5 to 10 years through this exploration?
Well, I would very much like to test the lunar cataclysm hypothesis and or the inner solar system cataclysm hypothesis. And this is this idea that the Earth and the Moon, and for that matter the other terrestrial planets, was severely bombarded roughly 4 billion years ago. That hypothesis was born with our analyses of the Apollo samples, but those missions were not designed to test that hypothesis. The hypothesis emerged rather serendipitously out of the samples that they collected. And so what I'd like to see is a collection of missions that test that, both because that was a period of time and a set of processes that completely reshaped the inner solar system, but also because those impact cratering processes were occurring at the very moment that life seems to have originated on Earth. And so we've been wondering to what extent there may be a link between these geologic processes and the evolution of biologic processes on the Earth and potentially elsewhere in the solar system.
Now, just as a reminder for people who are joining us late, you are tuning in to the CLSE monthly hangout, except in August. We're going to skip August due to the International Astronomical Union meeting. With us today is the principal investigator of the CLSE node, which is a survey node down in Houston, David Kring, and you are welcome to ask us your questions using the Q&A app, which is available in any YouTube window that you're watching this on the internet. I do see that we have one question coming in from Adam Synergy, who says, I did some digging before the hangout and found a very interesting paper outlining a lunar L2 farside mission. Is this something that David can explain?
Absolutely. As hopefully everybody knows, NASA has built a new crew capsule. It's called Orion. This capsule is designed to carry crews of up to 4 astronauts to deep space, that is well beyond low Earth orbit where the International Space Station exists today. And it was a very successful test in December of 2014. The next mission is going to be called Exploration Mission 1, and that will launch the Orion capsule in orbit around the moon, and it will then return to Earth. And then Exploration Mission 2, which is right now scheduled for 2021, will actually carry crew into the moon. They'll orbit the moon before returning to Earth. Now, once that capability is established, we will then have the capacity to conduct a number of cislunar missions. And so
Can you explain what the word cislunar means?
Cislunar means missions in the vicinity of the Earth-Moon system. Okay, and one of the missions that we're taking a very hard look at is a mission in which the Orion vehicle swings around the moon to a point that is gravitationally stable on the far side of the moon. This is a Lagrange point, or L2 point, and a vehicle, a spacecraft at that point doesn't require much energy to stay at that point. And so the Orion spacecraft, if it reaches that point, can very easily maintain its position above the lunar far side. That's really attractive because from that position, the crew on Orion can maintain communication with Houston while also maintaining communication with a robotic asset on the lunar far side. And from a science point of view, this is incredibly exciting because we've never explored the far side. There's never been a vehicle that's, crawled around, roved around, on the far side. It is completely unknown terrain except what we've been able to deduce from orbit. And so in a concept that we've been exploring, a robotic vehicle would be launched. It would go into a station-keeping position near the moon. Then crew would be launched in Orion. Once they were safely launched, the robotic asset would be landing on the lunar far side, preferably in the Schrödinger impact basin, and begin collecting samples. Crew would then make their way to the L2 position above the lunar far side, maintaining a communication relay between the robotic rover and Houston, even help drive the rover on the far side to collect those samples, and then the samples would go in an ascent vehicle. They'd be launched to that L2 position where the astronauts would pick them up and then bring them back to Earth. It's an incredibly exciting mission. It has the potential of addressing many of the highest priority science objectives as articulated by the National Resource Council, while also testing the exploration systems in such a way that it will make it easier to move forward with even more complex exploration missions, either in the vicinity of the moon or elsewhere in the inner solar system.
And just to clarify, when you refer to the NRC recommendations, you're referring to the Planetary Science Decadal Survey, I believe.
No, I'm not.
Oh, okay.
So several years ago, now almost a decade ago, NASA went to the National Research Council and said, if we do go back to the moon to explore the moon, what should our priorities be? And this generated an NRC, National Research Council report in 2007 called The Scientific Context for Exploration of the Moon. And it is a list of 35 science investigations in a prioritized order for what we should do if we go back to the moon. Now, there are other NRC reports, and you referred to the decadal. The decadal report asks a different question. It says, what type of science should we be doing with a specific type or types of missions? So it is a more narrowly focused or constrained set of questions, whereas the scientific context for exploration of the moon is a broader view of what should be done on the moon.
Thank you. It was unclear which of the studies, and I had assumed wrong, and I'm guessing some of our audience had as well, so thank you. I'm getting more questions in from our audience, and this one's actually one that I think is every scientist's dream. Kyle Carmichael asks, out of curiosity, would it be more of a technical issue or a money issue to run a sample return mission with the capability to return significant core samples of 10 to 20 meters deep? Just imagine a 20-meter deep core sample of Vesta.
Well, at the moment, we don't have the technical capability to drill that deep with what I think people think of as a traditional coring device. I'm in Houston, where we have lots of companies that drill rather routinely into the crust of the Earth, but those technologies are not immediately or easily transferred to more distant locations. But that said, I've always pointed out that nature has already drilled into planetary surfaces for us. That is what an impact crater is. And in fact, that's one of the techniques that we, and by we now I mean the planetary geology community, taught the Apollo astronauts. And they taught them at places such as Meteor Crater in northern Arizona. The astronauts did not need to drill into the lunar surface to excavate several hundreds of feet into the lunar surface. All they needed was a crater the size of Meteor Crater to have drilled into the lunar surface for them. So for example, the Apollo 16 astronauts went to North Ray Crater, very similar in size to Meteor Crater in northern Arizona, and were able to sample the subsurface of the moon to a depth of several hundred feet by simply looking at the rocks thrown out of that crater.
And one of the awesome things is, since the gravity is so much lower on these small bodies, when a crater impact forms, it doesn't fill in. So you can actually get away with having deeper craters with smaller sizes, if you will. And so sometimes the low gravity really helps us out. So tied in with all of the science and exploration goals that you have, there's also a desire to work on disseminating results out to create a more educated public. Mm-hmm. How do you weave that thread through everything that you do?
About 100 different ways. So Andy is sitting here laughing a little bit too. We try a lot of different ways to communicate material to the public. We train teachers, and teachers then can talk with a lot of students. We do a lot of online activities. Whenever possible, we do television or science documentary interviews. We put a tremendous number of resources online. For example, just 2 weeks ago, maybe 3 weeks ago now, we released a new flyover video. An earlier question that I was asked is to actually describe a mission of crew to the L2 position above the lunar surface. This recently produced flyover does exactly that. It takes you from the Earth to the moon. It shows you the South Pole Aitken Basin using the latest imagery. It then flies you down to the Schrodinger Basin, right to the landing site that we've been studying for the last 4 or 5 years. And I have to say that it's eye-popping. It is. I don't think people appreciate how beautiful the moon is, because many of the people still have this scratchy, snowy television view from the Apollo era in their minds. But with the new high definition or just simply high resolution imagery that we have, it really does paint the moon in a completely new light. So those are the types of, some of the types of ways that we try to engage the public and explain to them what it is we're doing, and I think more importantly, what is possible in the future with the missions that we would like to fly.
And we will work to get all of these videos linked in to the show notes that we will put up on YouTube as well as on Google+. And if you'd like to find not just the flyover video, but all of the multimedia that's coming out of CLSE, They trick you. It's not at a CLSE website. It is actually at the home institution, which is www.lpi.usra.edu, and that stands for the Lunar and Planetary Institute. Can you explain a little bit about how the center and LPI all fit together within USRA?
Oh, sure. The Lunar and Planetary Institute has a tremendous historical heritage. It was actually founded by the White House, President Johnson, and chartered by the National Academy of Sciences, originally called the Lunar Science Institute, to both assist NASA with the Apollo program and to be an interface between the university or academic community and NASA. After Apollo, its portfolio expanded and it became the Lunar and Planetary Institute. Now, that institute, as I mentioned a moment ago, was designed to work very, very closely with NASA. And so it was situated immediately outside the gates of the Johnson Space Center, at the time called the Manned Spaceflight Center. And so there's been a tremendous collaboration between the LPI and the Johnson Space Center over 40 years. And so a few years ago, and it was in 2008 or 2009, I can't actually recall, but the LPI and the JSC got together to create this new Center for Lunar and Science Exploration that really builds on that heritage and provided a way of focusing studies on the collisional evolution of the inner solar system, including the moon, and the exploration of those planetary surfaces.
And URLs, as it happens, the URL for this joint venture just happened to land on the LPI side of that collaboration, but there are wonderful tools on both sides and on both sets of websites. So our time is starting to run down. We've covered a whole lot of ground today, and I didn't mean that to be as punny as it came out. What are some of the things that you'd like our audience to walk away with, or some words of inspiration that you might want to leave them thinking about as we continue our explorations of the inner solar system?
Well, first of all, as a visual and audio way of being inspired, I do encourage people to go and look at a couple of our flyovers. In particular, there's a flyover called From the Earth to the Moon that I think is absolutely outstanding in that sense. I show that sometimes in public lectures, and I look out in the audience and I actually see tears in some people's eyes. But I hope people understand that it is time to get out of low Earth orbit. We went to low Earth orbit and built a space station for very good reasons. We needed to learn how to operate and build things in space, but that's done. I think it's important to reestablish the capability to explore beyond low Earth orbit in deep space, and for a variety of reasons, both scientific, architecturally, practically. The moon is a great place to begin those exploration efforts. It's a very exciting place to go. The landscapes there are so dramatic. People just don't understand that the landscapes there kind of make the Grand Canyon look a little bit puny. So if your eyes have been widened by standing on the rim of the Grand Canyon, you should take a look at some of the views available on the lunar surface. So I hope that those people listening are as excited as we are here at the LPI and JSC with human exploration, and are anxious to see us recover the capability to explore the moon and other destinations beyond the moon.
And this brings us back to that wonderful potential that we're looking at with all the heavy lift rockets that are being developed to return to the moon, to go to the asteroids, to go probably to Phobos or Deimos first before we go to the surface of Mars. If you had to pick the one you want to see completed first, can you pick just one?
Oh, well, for a variety of reasons, we needed to go to the moon first. And in fact, I was once doing a National Public Radio interview where this topic was being discussed, and it had a call-in feature just as your show does. And I was pleased that Apollo 17 astronaut Senator Jack Schmitt called in and pointed out that the fastest way to Mars is via the moon. And I think he was exactly right, and I hope we get to the lunar surface sooner rather than later.
That sounds good. And for those of you who may not know, there is actually a Google Lunar X Prize Hangout that will be next Wednesday. And the folks on the commercial side, they're looking to get their little rovers landed within the next year. And this starts to change the dynamics of how we get back to doing science, although it's probably going to be NASA and one of the heavy lift rockets that gets the humans there first. This has been an excellent tour de force through the inner solar system. Where can people follow your work in particular if they want to follow up on your explorations?
We post things, we update every time a new paper is published, every time a new exploration report is published. It is listed online at the Center for Lunar Science and Exploration's website. And so people can follow our progress there. I guess that would be the starting point.
That sounds good. Well, thank you so much for joining us this evening, and I hope that we see you again in a future Hangout as we continue to learn more about all the things that you as principal investigator are helping to facilitate happening. So thank you so much, and everyone, our next Hangout is going to be same time, same place, September 1st, and I believe that we are going to be hosting guests from the International Observe the Moon Night team and learning how all of us who share one moon can share one global celebration. So thank you, everyone. Have a great morning, afternoon, evening, wherever you are in the world. Thank you.